All right, get ready, because today we're going deep on Euler's 36 officer problem.
Euler's 36,
Yeah,
officer problem.
it's a mathematical puzzle
Mhm.
that has been perplexing people since 1779.
Wow.
So you might be wondering, what does some, centuries-old math problem have
Yeah.
to do with me?
Yeah.
But get this.
Okay.
It was considered impossible to solve
Really?
until some researchers recently figured out a way to bring in
Oh, wow.
quantum mechanics.
Quantum mechanics to solve it.
Yeah, are you intrigued?
Absolutely, I'm intrigued.
You knew you would be.
Yeah. So what makes this problem so fascinating is that it actually seems pretty straightforward at first.
Okay.
So imagine like a 6x6 square,
Yeah.
like a chessboard,
All right.
and you're trying to arrange 36 officers.
Mm-hmm.
Each officer has one of 6 ranks and also belongs to one of 6 different regiments.
Okay.
The rule is no row or column can have 2 officers with the same rank or the same regiment.
So kind of like a super strategic Sudoku.
Right.
There's got to be a catch.
There is a catch.
Right.
Euler himself couldn't find a solution.
Wow.
And later mathematicians proved that it's impossible to solve using like classical methods.
What?
No matter how you arrange those officers, you'll always end up with a conflict somewhere.
Oh.
But that's where quantum mechanics comes in.
Okay.
Recently, researchers have claimed to have found a solution by making the officers quantum.
Okay, so how do you make an officer quantum?
Well, they don't give them superpowers or anything,
Right.
but they do have some quantum quirks.
Okay.
In the classical version of the problem, each officer's rank and regiment are fixed.
Yeah.
But in the quantum world, things can exist in multiple states at once.
Okay.
It's called superposition.
Superposition.
It's like a coin that is both heads and tails until you look at it.
So these quantum officers are kind of like blurry.
They're blurry.
Like they haven't decided on their rank or their regiment yet.
Yeah, it's like each officer holds the potential for all ranks and regiments simultaneously.
Oh.
It's only when we measure their position on the square
Yeah.
that they collapse into a specific rank and regiment.
Oh. Okay.
And here's the kicker.
Okay.
This fuzziness, this ability to be in multiple states at once, actually allows for a solution to this puzzle.
Oh, wow.
That's pretty wild.
That's mind-bending.
Yeah.
But I mean, how does that actually work?
How does that actually work?
Like, how do these quantum officers help us avoid those conflicts that made the classical version impossible?
That's where an entanglement comes in.
Entanglement.
Another mind-boggling concept
Okay.
from quantum mechanics.
Yeah.
Imagine you have 2 coins that are linked.
Okay.
When one lands heads, the other must land tails,
Okay.
even if you separate them
Right.
by a huge distance.
Yeah, I remember learning about this.
They stay connected in this way.
Like they're communicating instantly across vast distances.
You got it.
Okay.
Now imagine applying this to our quantum officers.
Right.
Their ranks and regiments become entangled. So measuring one officer tells us something about others.
Okay.
This allows for a really clever workaround.
Right.
It's like the officers are coordinating on a level that simply isn't possible in the classical world.
So they're kind of sneaking past Euler's rule
Sneaking past
without breaking it.
without actually breaking it.
That's brilliant.
It is.
So they used these quantum phenomena and were able to create an arrangement that satisfies all the conditions of the puzzle,
That's right.
which was mathematically
It's possible.
impossible with classical officers.
Classically, it's impossible.
That's incredible.
I know, it's amazing.
So they turned an impossible problem into a solvable one just by,
Changing the rules of the game.
changing the rules of the game.
With quantum mechanics,
Using quantum mechanics, yeah.
it's wild.
Okay, so they didn't just stumble on this solution.
No, they didn't.
They used an algorithm.
They used an algorithm to find it.
How did this algorithm work?
Well, it's a bit nuanced. They started with a near solution,
Okay.
a classical arrangement with just a few conflicts.
Okay.
Then they used the algorithm to iteratively tweak the entanglement and superposition of the officers, guiding the system towards a valid quantum solution.
Okay, so they're like strategically nudging these quantum officers into place.
That's a good way to think about it.
Yeah, I can't even imagine the complexity of this.
It's pretty complex.
Yeah.
But they found a solution.
So did this solution reveal anything interesting?
Yes.
Beyond just proving that it's possible?
Beyond just proving it's possible.
Like, were there any hidden patterns?
Yeah, there were some interesting features of the solution itself.
What did they find? You mentioned that the solution itself had some interesting features.
Yeah, so one of the most striking discoveries was the role of the golden ratio.
The golden ratio.
That famous number, 1.6188.
Okay.
That seems to pop up everywhere.
I've always been fascinated by that.
From seashells to spiral galaxies?
Yeah, it's like this
It's everywhere.
secret code underlying all the beauty and harmony of the universe.
Right.
What's it doing in Euler's officer problem?
That's what's so remarkable about this finding.
Okay.
The coefficients that describe the degree of superposition.
Superposition.
And each officer's quantum state. Remember how they're a mix of all ranks and regimens simultaneously?
Right, right.
Well, those coefficients are all related to the golden ratio.
Hold on.
It's pretty wild.
So the golden ratio is like woven into this quantum solution.
It's woven into the solution.
But what does it mean?
Well, it suggests that this solution isn't just some random arrangement.
Okay.
The presence of the golden ratio hints at a deeper structure.
Okay.
A kind of mathematical elegance that underlies this,
Yeah,
seemingly chaotic quantum system.
that's why.
And it's particularly relevant because this solution also happens to be something called an absolutely maximally entangled state, or AME for short.
AME state. Okay, I've heard that before, I think.
And you might have heard of it.
What is it? What is an AME state and why is it so special?
Okay, so AME states represent the ultimate limit of entanglement.
Oh, wow.
They're configurations of quantum objects
Okay.
where the correlations are as strong as they can possibly be.
Okay.
Imagine those two linked coins again.
Okay.
With AME states, you can have that perfect heads-tails correlation even with multiple objects,
Okay.
all intertwined in this intricate quantum dance.
So it's like an extreme form of entanglement
Extreme entanglement.
where everything is connected in the most intense way possible.
That's right.
That sounds pretty powerful.
Ooh, it is powerful.
Yeah.
And it turns out that this golden ratio-infused solution to Euler's problem is one such AME state.
Oh, wow.
This connection between AME states and the golden ratio
Yeah.
is particularly exciting because AME states are highly sought after in the world of quantum computing.
That's right. I remember hearing about AME states in the context of quantum computers.
Yeah.
How do they actually help?
So AME states are incredibly valuable for something called quantum error correction.
Quantum error correct.
Quantum computers are notoriously fragile.
Right.
Any tiny disturbance
Yeah.
can disrupt the delicate quantum states and cause areas in a computation.
It's like trying to build a house of cards.
It's exactly.
Like,
It's
or-
very fragile.
Right.
But AME states, with their highly structured entanglement, offer a way to protect quantum information
Okay.
from these disturbances.
So it's like a safety net.
It's like a safety net that can catch and correct errors as they occur.
So this golden AME state
Yes.
that was discovered through solving Euler's officer problem
right.
could potentially lead to more robust quantum computers.
More robust and reliable quantum computers.
So we have this amazing connection between this theoretical math puzzle
I know, it's amazing.
and cutting-edge technology.
It highlights how exploring these seemingly abstract problems
Yeah.
can sometimes lead to unexpected breakthroughs.
In other fields.
In other fields, absolutely.
But are the implications?
The implications might go even deeper than that.
Okay, now I'm intrigued. What else could this be connected to?
Some physicists believe that AME states, especially this one with its connection to the golden ratio,
Yeah.
might offer clues about the very nature of reality itself.
Okay.
They're exploring the possibility that AME states
Mm-hmm.
could be fundamental to the structure of space-time.
Hold on. Are we talking about the fabric of the universe here?
We are talking about the fabric of the universe.
The stage upon which all of reality plays out.
That's right. Imagine space-time not as a smooth, continuous background,
Okay.
but as a network of interconnected points,
All right.
each one entangled with others in this vast cosmic web.
Okay.
And the patterns of entanglement,
Yeah.
particularly those found in AME states, might determine the very geometry of space-time,
Okay.
how it bends and curves,
Yeah.
creating gravity, shaping the universe as we know it.
So instead of space-time being some kind of fixed container for the quantum world,
Right.
it's actually like emerging from the quantum world itself.
It's emerging from the quantum world.
Yeah. So it's like the universe is built from the ground up with entanglement
Entanglement as the building block.
as its building blocks.
That's the idea.
That's a pretty radical shift in perspective.
It is a radical shift.
It challenges everything we thought we knew
It challenges our classical intuitions
about the nature of reality.
of reality.
Yeah, so if space-time is woven from entanglement, what does that mean for our understanding of time itself?
Time, the eternal enigma.
Right.
If space-time is an emergent property of entanglement,
Yeah.
then time might not be the absolute linear flow we perceive it to be.
Okay.
Some theorists propose that time emerges
Okay.
from the evolution and interaction of these entangled states.
So time isn't a separate fundamental aspect of the universe,
It could be that time is not fundamental.
but like a consequence of how information flows and changes
Information flow.
within this cosmic web of entanglement.
That's the idea.
That's a lot to take in.
It is a lot to take in.
So if time isn't absolute, what does that mean?
What does that mean?
Does that mean our past, present, and future are all entangled in some way?
It's possible.
Could we potentially influence the past or future by,
That's a big question.
manipulating entanglement in the present?
That's a question that a lot of people are thinking about.
Okay, now we're getting into sci-fi territory.
A little bit sci-fi?
But it's a thrilling thought.
It is a thrilling thought.
So how do we test these ideas?
How do we test these ideas?
And to figure out if this entanglement-based view of space-time is actually correct.
That's the million-dollar question.
Right.
While directly measuring the entanglement of space-time is beyond our current capabilities.
Yeah.
Physicists are searching for indirect evidence.
What kind of evidence?
One promising avenue is to look for subtle signatures of quantum gravity
Okay.
in the cosmic microwave background radiation,
Oh.
the faint afterglow of the Big Bang.
So those whispers from the early universe
Whispers from the early universe.
could hold clues about the quantum nature of space-time?
They could hold clues.
Wow. What would those signatures look like?
So they'd be extremely subtle patterns in the polarization of the cosmic microwave background.
Okay.
Deviations from what we would expect if space-time were purely classical.
So finding these patterns
Yeah.
would basically be like finding the fingerprints of entanglement
Fingerprints of entanglement.
at the very beginning of the universe.
At the very beginning.
That would be huge.
It would be a strong piece of evidence
Yeah.
to support this new view of reality.
So some physicists believe that observing these patterns would provide evidence
It would be evidence.
for a deeper quantum level of reality
A deeper level of reality.
that underlies our familiar space-time.
That's the idea.
So it sounds like we are on the verge of a major paradigm shift
It's possible.
in physics.
It's an exciting time to be studying these questions.
Yeah, that could fundamentally change how we understand the universe.
It could change how we understand everything.
Yeah, and our place within it.
Absolutely.
It's amazing to think we started with a math puzzle,
I know.
and now we're talking about space-time.
It's incredible.
Yeah.
And the universe itself.
It's a wild ride.
Yeah, but before we go,
Yeah.
you mentioned that this entanglement-based view of space-time
Right.
could have some pretty wild implications.
It does. It really does.
So what kind of implications?
Well, the idea that space-time is woven from entanglement
Yeah.
opens up a whole Pandora's box.
Okay, so let's open that Pandora's box.
All right, let's do it.
If space-time is built from quantum entanglement,
Mm-hmm.
does that mean the universe is, in some sense, like
Yep.
a giant quantum computer?
It's a question that's been captivating physicists and philosophers.
Yeah.
It's a really tantalizing idea.
Yeah.
So at its core,
Uh-huh.
a quantum computer uses the principles of superposition and entanglement to perform calculations
Right.
in a way that classical computers can't.
Right, they use qubits,
Qubits,
which can be in multiple states at once,
multiple states.
unlike classical bits.
Right. Which can only be a 0 or a 1.
0 or a 1.
And that allows them to tackle problems much faster
So much faster.
than a classical computer.
Yeah.
So imagine scaling that up
Scaling it up
to a cosmic level.
to a cosmic level.
Are you saying that the universe itself?
Some physicists propose
Yeah.
that the universe might be engaging in a type of quantum computation
Wow.
with the fabric of space-time serving as the hardware
Okay.
and the interactions of quantum fields acting as the software.
So those quantum fluctuations that we've been talking about,
The tiny ripples in the quantum fields.
could those actually be computations in progress?
It's a bold concept,
Yeah.
but it's a thought-provoking one.
In this view,
Yeah.
the evolution of the universe
From the Big Bang to
Yeah.
the present day.
is a grand cosmic computation.
It's a cosmic
It's
computation.
unfolding over billions of years.
Billions of years in the making.
That's an awe-inspiring thought.
It really is.
But if the universe is a quantum computer,
Yeah.
who's programming it?
That's the big mystery.
Right.
What is it trying to compute? We don't know.
We just don't know.
Some physicists speculate that the program might be encoded
Okay.
in the laws of physics themselves.
So the laws of physics are like lines of code
Lines of code.
that dictate how the universe operates.
That's one interpretation.
Wow.
Others propose that the universe might be constantly learning,
Okay.
evolving, adapting its computations over time.
A learning universe.
A learning universe.
What kind of possibilities does that open up?
Well, for one,
Yeah.
it suggests that the universe might be more dynamic and creative than we thought.
Okay.
It might not be simply following a fixed set of instructions,
Right.
but constantly exploring new computational pathways.
So the universe is less like a clockwork mechanism and more like a living, evolving being.
It's a beautiful way to put it.
That's adapting.
Experiment.
It's experimenting, yeah.
So what does that mean for determinism and free will?
Right. Are we just cogs in this machine?
Yeah. Or do we play a role?
In shaping the universe's computations.
Big questions.
That's getting pretty philosophical.
It is. It really is.
But it seems like the more we learn, the more questions we have.
More questions.
But I guess that's what makes science so exciting.
Absolutely.
This constant pursuit of knowledge.
The pursuit of knowledge.
This never-ending quest.
To unravel the mysteries.
To unravel the mysteries of existence.
That's what it's all about.
And it's been a wild ride from Euler's officer problem.
It's been amazing.
To the possibility of a universe-sized quantum computer.
It just shows you how these different fields can connect.
Yeah, and illuminate each other.
And lead to these incredible insights.
It's been an incredible deep dive.
It has.
Filled with these really complex concepts and thought-provoking questions.
Really makes you think.
Yeah, and to our listeners, we hope you enjoyed the journey.
I hope so.
Into the world of quantum mechanics.
It's a fascinating world.
And its unexpected connections.
Who would have thought?
To a centuries-old math puzzle.
Right.
Until next time.
Until next time.
Keep exploring.
Keep exploring.
Keep questioning.
Keep questioning.
And keep wondering about the universe.
And all its mysteries.
And all its mysteries.